Hi, my name is NellyRubio. My project today will be assessing erosion control suitability with NDII, a semi-arid watershed analysis. Watershed management in semi-arid regions is crucial to sustaining water availability for ecological systems and human health. Ecological degradation in the Southwest has been promoted by drought, cattle grazing, timber extraction, and beaver hunting. The removal of the key species and vegetation combined with annual monsoon rains accelerates channel erosion, carving deep headcuts into the landscapes. Ephemeral streams dominate the hydrologic network in semi-arid regions, and the degradation interrupts watershed health. Episodic storms like those experienced during monsoon season cause rapid runoff and mobilize nutrient-rich sediments that promote vegetation growth. Without the vegetation, the bare soil compacts and leads to more runoff events, creating a perpetual land degradation cycle. To counteract this indigenous traditions of land stewardship included the implementation of rock detention structures and erosion control structures. This method is not only cost-effective, but anecdotally proven to maintain watersheds. Quantitative data and scientific approaches to these structures are sparse, with only a few studies on NDVI analysis post the rock dam installations. Using remote sensing can not only monitor the success of these structures, but can aid in creating a scalable solution for watershed management. In this study, we will be discussing the utility of normalized difference infrared index as a proxy to soil moisture used to identify areas of low infiltration that would benefit from restoration planning. Normally, NDII is used to quantify leaf content, but it can also be used as correlation to root zone soil moisture. The sensitivity to changes in canopy moisture, even in sparsely vegetated areas, makes NDI more applicable versus NDVI, which is compromised in cattle grazed landscapes. One popular structure is the One Rock Dam. I'll be referring to it as the ORD from now on. An ORD has benefits to its construction. It is a simple structure that can have major impact on stream rehabilitation. These structures are only one rock high and have a splash apron to mitigate potential pooling, avoiding further degradation. ORDs work by slowing down the water flow, which promotes soil infiltration and recharging groundwater. The structure also aids in containing nutrient-rich sediments that promote vegetation taking root. After some time, the ORD will have raised the eroded channel bed and a new structure can be placed above to continue the restoration process. Using remote sensing and terrain analysis, the study aims at identifying suitable zones for ORD placement. Sorry. The study aims to answer two questions. Can NDII be used to identify zones with low soil moisture and high suitability for ORD placement? And two, do NDI trends at identified zones correlate with precipitation data collected from rain gauges? See, our study area will be concentrated in the Walnut Gulch Experimental Watershed. It is a highly researched area used in part by the Long-Term Agro-Ecosystem Research Network and the Southwest Watershed Research Center. This area was chosen as a study zone for the availability of precipitation data from its many rain gauges. The watershed is an ephemeral tributary to the San Pedro River on the west side of the study area, and geologically, the watershed is on a basin and range province and is an actively eroding alluvial pan with a deep alluvium layer. My workflow consists of a terrain analysis for logistical and geomorphic criteria and a raster analysis for seasonal NDI variation. Using Landsat imagery, I'll be able to identify low infiltration zones, which will go in use for my final ORD suitability map. The first step taken was to do a watershed delineation. Used our main outlet flume from the Walnut Gulch experimental range as our pour point, and using fill, flow direction, flow accumulation, and snap pour point, I was able to process the raster to outline the watershed boundary. Raster analysis. Precipitation data from the last decade was pulled from the rain gauge is from the Walnut Gulch. We were able to identify 2020 as the driest year at 8.71 centimeters of rain and 2022 as the wettest at 37.9 centimeters. Using Landsat images from pre and post monsoon seasons for each year in an NDII analysis, we identified areas exhibiting chronically low infiltration during variable precipitation. Using Terra in RStudio, I classified the NDII changes from pre and post monsoon. As you can see for 2020, which was the driest year, there are a higher number of values within the moderate increase class, whereas 2022 had more stable values during a wet season. This imposes the inference that antecedently dry conditions are highly susceptible to any amount of precipitation versus a more saturated ground will remain stable. Due to this high result of stability, we can infer that the stable zone could benefit from further infiltration, considering we are in a semi-arid region. Using ArcGIS Pro, I combined a raster of the stable, moderate decrease, strong decrease in NDII values, and that yielded about 73 hectares of low infiltration zones. These would be used in our final suitability. Terrain analysis. Success and longevity of an ORD is determined by proper placement. Proper placement takes into account geomorphic parameters, and accessibility to placing the ORDs is a logistical matter, considering that installation is fueled by manpower. Thresholds for both of these factors were taken into account. Ideal slope and velocity thresholds were implemented to create ideal candidate rasters that will ensure the longevity of the structure and avoid further degradation. Without these components, a structure can be washed away or topple over, or even worse, cause pooling and erode the banks, degrading the stream and causing more ecological damage. From a technical manual for ORD placement, we determined that 3% was an ideal slope for these structures. So we have a threshold from 2 to 4% slope, which yielded us about 3,175 hectares of viable slope area. And our threshold for our velocity was 0.2 meters per second and 2 meters per second. We avoided anything below 0.2 to avoid pooling, and anything above 2 was considered unrealistic. Here we got the streams within that viable velocity range. Logistics are crucial to the success of any project. So using manpower to build these structures creates questions on how easily will it be to traverse this land, and will we have access to roads to carry supplies in case they're not readily available within the site. Considering that the Walnut Gulch is an alluvial fan, terrain ruggedness is pretty moderate, so we consider that less important than the distance from the roads. Here we can see that the eastern portion is less connected from the roads, and the western side has a lot more access to roads. So we want to keep within the green zone to be able to access these locations most easily. We kept that on our suitability at a 2.5 so that we stay within the proper green zones. Suitability analysis. So here we have a map of using our four components. We used ideal slope, ideal stream velocity, our cost surface analysis, and our low infiltration zones. When we calculated this, we calculated that these 5 zones would be the best priority points for ORD placement. And then just to compare, if like say we did not use NDII, I did a suitability that points out that we would have 454 zones to target. This is a big project to take on, especially as just a starter point on developing a scalable approach to finding areas for these ORDs. It would take a lot of time and a lot of resources. So narrowing it down is best idea, but it does take into account that this drastic change can have its trade-offs, like failed performance due to unpredictability of soil or climate conditions. So this is more of a pilot implementation program where we can use these zones to put ORDs within proximity of each other. So you're not necessarily just putting one, you're putting a few within proximity to enhance the success rate. To validate this model, we compared the NDII validation moisture values with the rain gauge data from the Walnut Gulch's rain gauges. We were able to use a buffer of 1,000 meters to make sure that the precipitation experience at these rain gauges was similar to the precipitation at these priority zones. With that, we were able to pull the rain data for the nearest rain gauges. Here we have a table where we joined out the NDI values and the precipitation values at each priority point. This is the closest rain gauge, the distance to the gauge, and so we can see here that the NDI values on 2020, which was the driest year, have a positive value, even though the precipitation value is far less than the precipitation in 2022, which was our wettest year. The NDI values of 2022 were actually negative. This allows us to see that there's more of an inverse relationship where NDII is most useful during periods of high drought and less useful during periods of higher precipitation. Again, our objectives are to answer these two questions, and our questions again were: can NDII be used to identify zones with low soil moisture and high suitability for ORD placement? And do NDII trends at identified zones correlate with precipitation data collected from the rain gauges? We were able to use NDI to effectively identify chronically dry zones across both wet and dry years. It was a narrowed down approach, but does create an implementation program where you can find areas within distance of these priority points for these ORD placements. NDI's trends were inversely correlated, so we were able to see that NDI trends are most useful during periods of drought. During periods of high precipitation, it is less accurate, and it's useful to use mostly during periods of drought for identifying these low infiltration zones. A way to further enhance this project would be to use fine scale resolution imagery for better channel detail. So if we use this fine scale detection, we can determine stream incision, channel width variability, and riffle pool sequences to improve the placement and longevity of erosion control structures. This project just has a way of helping to empower landowners to make more informed decisions on where they're placing these structures so that they don't cause any more damage. But we can take into account that field validation is critical for these structures. Field evaluation allows practitioners to assess real-world conditions such as channel morphology, soil health, and vegetation dynamics. These field evaluations help to ensure that these proposed interventions enhance the ecosystem without causing more unintended degradation. In all, NDI proved useful in narrowing down zones of low infiltration that are more readily in need of restoration. So I believe that using NDII for further evaluating zones will prove useful in more scalable approaches, as long as they're used in conjunction with field evaluations to ensure that the land is in actual characteristics of needing these restoration structures to be implemented. And that's all I have for you today, and thank you.